Welcome back from the latest networking break, once again sponsored by W Grace. I hope you had time to do your one-to-one meetings or to visit the booths. Our next session is focusing on achieving higher profitability, and we have three presentations, four speakers. First up, we have a presentation from Ina Grupa, and we have two presenters. We have Goran Pepic, technology senior expert, and he will be joined by Christian Drozdek, who is manager of production. And their presentation is a case study focusing on vis-breaking residue processing in the CSAC refinery. Our second presentation is from Vincent Frater, who is a technology manager at Perna, and his presentation is focusing on another way to process the bottom of the barrel with quality bitumen production. And to close out the session, we have a presentation from IPCO, who have been kindly sponsoring our Q&A sessions. It's from Marvin Petit-Homme, who is sales manager at IPCO, and his presentation will be focusing on handling carbon-rich residue to form clean solid fuel. So a warm welcome to all our presenters. Please enjoy the session and send in those questions. Thank you very much.
Thank you for your introduction. So, vis-breaking residue processing in CSAC refinery was successfully done on delayed coking unit. So, several test runs have been executed in 2018 and 2019 to investigate the possibility of processing this non-standard feedstock on delayed coking unit. Results of those test runs will be shown in this presentation. Some basic information about the unit. The unit was built in 1967. Annual capacity of the unit is 267 kilotons per year. Some major revamps happened in 2013 when new coke drums were installed, and in 2016 closed blowdown system was introduced and put in operation. Regarding possibility of processing vis-breaking residue, in 2018 there was a first test run. It was actually a co-processing. Basically, we processed 50% of the vis-breaking residue bottoms and 50% of the standard feed, which is a vacuum residue. And then in 2019, with the support of the external company coking.com, we managed to process 100% of the vis-breaking residue. And this mixture contained 90% of the vis-breaker bottoms and 10% of the aromatic cutters. The unit is originally designed to process vacuum residue. So the vacuum residue is first preheated in the convection section of the furnace up to 280 degrees, and then it's sent to the fractionator where it quenches the overhead vapors coming from the coke drum. This combined feedstock is then sent to the radiant section of the furnace, and it's heated up to almost 490 degrees and sent to the coke drums. All products from the main fractionator column are light and heavy gas oils. They are used to produce diesel, and overhead stream containing LPG and coker naphtha. It is splitted in gas concentration unit. This unit has a 24-hour coke drum cycle. Basically, steam to the fractionator and closed blowdown system takes approximately 4 hours. Water quenching and draining takes 7 hours. Top and bottom unheading 1 hour. Coke cutting 5 hours. Reheading, steam test, and purging approximately 1 hour. In altogether, drum warm-up takes approximately 6 hours. Regarding some major equipment, switch valve is a manually operated valve. Top and bottom unheading system are also opened manually. Coke cutting pump uses high pressure steam for driven. Unit is controlled with the pneumatic system, which was upgraded in 2016, and we use now DCS system. Coker furnace is a cabin type, natural draft. It has 16 tubes in the convection section and 76 tubes in the radiant section. It has 2 passes. It has 20 combined horizontal burners. Typically, coil inlet temperature is approximately 370 degrees and coil outlet temperature typically 490 degrees. Pressure inlet to the coker furnace is between 17 and 21 bars. Those are the basic information, and now my colleague Goran will introduce about the test run results. Thank you very much.
Hello everyone, I will continue with the description of test run process itself. In order to carry out test run in a safe way, we consider the impact of fresh feed quality, process parameters, and human interactions and communications. Human interactions and communications is important since there are a lot of manual operations on the plant itself. So, first, feed quality during test run is shown on graph. On the graph, you can see relation between SARA analysis for fresh feed and for combined feed to coke drum test run. This is very important to know and choose right actions at proper time. You can notice that relative higher aromatic and asphaltene content in visbreaking residue feed in comparison with domestic feed. Percent of visbreaking residue in the feed is rise day by day after we confirm that unit is in safe operation. Also, significant difference between density for domestic feed is density is average 1970 kilogram per cubic meter, and the end of test run visbreaking residue fresh feed has almost 1000 kilogram per cubic meter. Also important difference is in sulfur content, which was up to 3.28%, and condensate carbon residue number. Our original coker design is up to 10, and now in feed it was up to 18. CCR is in direct correlation with coke yield, if, of course, other parameters are constant. So, most important process parameters during test run was recycle ratio and coil outlet temperature from process heater. These graphs show correlation between recycle ratio and microcarbon residue or condensate carbon residue in fresh feed and in combined feed during the test run. If we connected microcarbon residue with coke yield, also I mentioned in previous slide, it means higher microcarbon residue will result in higher yield of coke. This is the rule of thumb. You can see what we did. We manipulate with recycle and directly influence on coke liquid yield distribution while paying attention to the process furnace and coke morphology. Why this is important? Manipulation with recycle and with coil outlet temperature due to feed changing during test run ensure stable continuous operation. This slide explains how much coke is in coke chamber comparing to the industry standard. We conclude that we are below industry standard and we have enough space in coke chamber. But next slide will explain why we need to make some other changes. This one explains why human interaction and communication was also important in combination with process parameter and feed quality. On slide is most important human interaction from the coking operator, and we measure his performance. Performance of this man is crucial to be on time with coke drilling and cutting to enable 24-hour cycle and continue operation of the unit. As graph show, in the middle of test run, we have very hard coke. It means slowest drilling and cutting, which cause prolonged cycle time. This was indication that we need to take action and correct parameters, decreasing recirculation further and lowering the coil outlet temperature in order to return to normal cycle time. As a result of our works, during test run yield structure was for LCGO or light coker gas oil, wet gas to gas concentration unit and unstabilized naphtha stay almost stable, while heavy coker gas oil yield decreased and coke yield increased. Increase of coke yield was expected due to higher microcarbon residue in this breaking residue feed. On the right corner, you can see that model has been developed that correlate with actual unit data, and in future we can predict and optimize yield of products based on feed and process parameters. As a safety concern, I want to point out again that during operation we very carefully monitor morphology of the coke from each chamber each time the process parameter and feed quality were changed, and confirmed that higher amount of this breaking residue feed doesn't change coke morphology. In practice, higher amount of asphaltene and higher microcondensation residue can lead to change in coke morphology from the sponge coke to shot coke. Shot coke is not acceptable for our site. Regarding coke quality, on the right table, you can see that expected sulfur and metals were increased, but in acceptable limits. To summarize, during this test run period, this breaking residue feed blended out 90% of these breaking components and 10% of aromatic cutters were processed on CSAC delay coker unit very successfully. Ratio of this feed was gradually increased during test run period up to, I can say, 100%. This test run also showed that 24 hours designed CSAC delay coker unit cycle was maintained, ensuring continuous operation of the unit. And future challenges, we need to increase inspection dynamics of wall thickness of the equipment due to high sulfur content, implementation of recommendation to increase process safety that we found on the unit, further optimization of process parameters to improve yield structure, if it will be possible. That's all from us. We appreciate that we had this opportunity to present you and to be part of this event. Thank you.
Good afternoon, everybody. It's a pleasure to speak to you, that you are on board to speak about another way to process the bottom of the barrel, and I will present the Perner bitumen technologies. Thanks a lot for EPC for the organization. It was a great up to now. So a few words about Perner Engineering. We are a private Austrian company with approximately 500 engineers working in any kind of engineering projects. We make piping, and mechanical process, E&I, and of course also architecture. We are an engineering partner of many refineries and petrochemical companies in Europe and Russia. We have offices in Austria, in Germany, in Russia, in Ukraine, and Romania. And we are with our bottom of the barrel technologies active worldwide. For example, a lot in the Middle East in this time, in Saudi Arabia, in Iraq. We have a lot of licenses in India also, and a few other countries. Now, what will be the main topic of our presentation today is the processing of the bottom of the barrel and bitumen production. You see here the flow sheet of a refinery using, after the distillation, an SDA and a Bitrox unit with a loop plant processing the DAO, producing the SDA unit. Of course, if you don't have a loop plant, you have a nitro cracker or you have an FCC. it can work the same way. It's just that you have to use a different branding of pitch and VR and VGO and extract or other components for the bitumen production. What's special in our solution is SDA and Bitrox. First of all, the using of SDA and bitumen blowing is a well-known process. It's done in a lot of refineries in a proven way that it's working properly. Second point was really important is really cost-efficient technologies because they are both not so expensive like cokers or hydrocrackers. You don't need any hydrogen, so it's really important on the OPEX also. And you don't have any residue out of your refineries because you are processing the pitch and perhaps the rest of the VR for the bitumen production. So it's really important in these days to have use of all the components in the refinery. If you intend to produce bitumen out of the pitch, you have to take a compromise. You cannot use a yield of 60, 70% of your SDA using pentane or hexane, even a solvent, and then think you will use the pitch for bitumen production. No, you have to find a way, having a proper yield, perhaps 40, 50%, to have a good pitch for the bitumen production afterwards. And it's where we have our specialty because a lot about bitumen, we know a lot about SDA, and the combination is unique. Now, let's start with SDA. How we are going into projects for SDA, but typically the first step is always to have to have tests in our units to start to see how is the VR. We analyze the vacuum residue first, of course, and then we make the first test with a fixed solvent ratio and solvent defined solvents, typically propane or a mix of propane and butane, to reach the equilibrium between DAO and pitch and have the first results. And these results are the basis for the simulation model to be able to design properly SDA. And a really important factor in this process, of course, is the SARA analysis, giving the saturates, aromatics, resins, and asphaltanes percentage in the VR, in the pitch, and in the DAO. So here you see a picture of our lab scale unit in Germany, in Leipzig, where you can see the autoclave on the left side and all the valves and everything to reach a proper equilibrium and to have the really important data for the simulation. So second step of the test, of course, is the simulation model. As everybody knows, we are using equation of states thermodynamics, and from basis from the figures we have from the tests, we are reaching with our modified model and Prausnitz a really good simulation to meet the data. That's of course the way. And what is special for us is that we have a lot of experience with heavy components. We have an additional model for the pitch viscosity. What is really important because the viscosity is always more an important factor also for the bitumen production. Of course, it's based on the DIPs between the different SARA components, and all of this is really important. But it's everything based on the results from the lab test to have proper simulation. Benefits, of course, as I said, now we have a really precise reproduction of the data from testing, so we can reach a perfect simulation. And then we can calculate the yield of the DAO and the solvent load and all the impurities for the DAO side. And on the pitch side, the important parameters like the composition, depending on the different families, and also then the viscosities and penetration and softening point, the next step to bitumen production. Of course, it's always based on the temperature, pressure, solvent rate, and solvent we use for the testing. But when we have that, we can then extrapolate on different other process parameters, like another solvent rate, another pressure, another temperature. And if necessary for studies, for feasibility studies, then we can use with similar residues. We have data in our database. We can forecast the SDA process also. The most important thing using this way is that we don't need too many trials because it's really time and of course our money consuming. Here, the few parameters are typically used for the quality of DAO and pitch. Where for DAO, it's clear are the metals and purities, the nitrogen purity also, and the CCR. Depending if you have an FCC, a nitrocracker, on a low oil plant, it's a different figures. For the pitch, of course, the penetration, softening point, paraffin content, and the last point is the viscosity. Paraffin content is really important for units running with really waxy crudes, because typically, waxy crudes and bitumen production, it's not really working. If you use the combination SDA and Bitrox, you can still reach a good bitumen quality, because you can take most of the waxes out of the pitch in the SDA. Now we will go to the bitumen production. For the few of us perhaps are not used for the bitumen production, how it is running. Typically, the feedstock we use for bitumen production is vacuum residue. Clearly, with some HVGO is necessary, but always more, in this topic of this presentation, is based on SDA pitch or residues from hydrocracker, from coker, or also aromatic extract, like in this case, coming from the low plant, or any other special component, as we call them. Then we are making testing in our facilities, so we present it afterwards, and we can reach the best possible solution for your refinery. On the product side, there is 3 big families of standards for bitumen. You don't find any specification with its okay worldwide. That's a huge problem. You have the penetration softening point family, like European standard or ISTM, which used a lot in the Middle East and in Africa. Then you have the viscosity family standards, which used especially in India and Australia. And the third one is the best application you can find for bitumen based on the performance, like you have in the US Sharp or New Zealand, but it's also the most expensive on testing and time consuming. So it's not still not used a lot. It's moving in this direction, because people are always being more interested to have good roads, because without infrastructure you have a huge issue in the country. That we say in many countries in Europe, perhaps it will be more in that way on time. Now, the second really important thing to know about bitumen production is the blowing diagram, which you can see here on the right. It's based on the penetration against the softening point. You have the straight on the left side. That's what you reach when you have a vacuum distillation. So it's a straight, because you cannot change anything chemically. It's a physical separation. And then you have the two curves. That's what we call the blowing curves. It's how you manage to reach your specification, penetration softening point specification. All these windows, the green one for road grade bitumen, the red one for industrial grade. And so you are able to produce bitumen according to specification, using in one curve only VR, the second curve is using a blend of VR and other components. For your information, capacity of Bitrox unit we installed in the past up to now, from 70,000 tons a year, that's really small, up to 1.2 million tons a year on the same site. That's really, really big units with. I will show afterwards a reference about that. So now about the Bitrox technology itself. Chemical conversion, clearly, because you have an oxidizing agent, is air. That's important. We don't have chemicals, we don't have catalysts, so the OpEx is really low. We are creating resins and asphaltanes that are not available at the beginning or from the VR. So that's really important, because you change the chemical composition feedstock. And it's allow a really high flexibility from a wide range of crudes. You can use more crude than the so-called bitumen crudes, that you can reach bitumen out of the vacuum distillation. How is it working? We have analysis of the feed components, VR, pitch, extract, VGO, or any other component we spoke before. Then we are optimizing the feed composition by pilot testing typically, and processing it in our pilot unit under specific pressure, temperature, and air rate to reach the product according to specification in the country of your base. If you are producing a lot for export, also for the standards in the exported countries. Here a little bit more details about the reactor. Is the core of the technology. Of course, in this case, it's really different of what you know from the past. It's a continuous reaction within a loop reactor, a shorter blowing time, because it's also working on a higher pressure. The herring production is gentle but really efficient on the bottom, so it's really important because the coke buildup is really minimized. Your really high yields, that's really important, 97, 98%. Of course, with proper design, we can control all the really important parameters like temperature, typically 250 degrees Celsius, and the pressure 2 bars over the atmosphere. The rest oxygen also is really low, so it's a really minimum risk of fire in the off-gas section. So a little bit more details. You can see here you have the agitator in the middle with stages, 3 stages, agitator and coalescence plates. The air is introduced on the bottom with 4 big pipes. So you have big bubbles at the beginning, then it's reacting, starting not too quickly, and then the bubbles are getting smaller and the hole is well agitated. And then when the bubbles are getting too small to avoid too strong reaction, then we have the coalescence plate to restart with bigger bubbles, and at the second time. And then we have the circulation of the VR of the bitumen that way. Here is introduced here, coming out here, on the top you have the off-gas going out. Now, as I said before, we are making pilot testing in our unit in Vienna. That is how it is looking like. It's also a service we are offering to our licensee, that we sell these pilot plants if they are intending to make research and development in their own laboratory, or if they intend to change the slate of the refineries, that we can test all of this. We have 2 different sizes of reactors. We can change every parameter, any kind of feedstock and reach any kind of product. And the whole system is recording everything on a PLC, of course. Now we'll show you a few references about our unit. First of all, the SDA. This reference is H&R in Hamburg, in Germany. This will be one of the first units we make for SDA. Started 2011 with quite a complete package on the delivery. On the other side, another references, it was the one started last year in Belarus, where we made the complete package from pilot testing, basic engineering, delivering of extraction column and other equipment, installation and be done on site. It's quite difficult for a German company to work competitively against a Belarus construction company, of course. Now, a few references about PITRAX. This one is the one we started, it's already 2 years ago for SOCAR in Baku in Azerbaijan. It was an EPCS contract, so we made the whole licensing, pilot testing, basic and detail engineering, supplying all the itemized equipment, and then we supervised the construction in the name of SOCAR, and then of course the startup of the unit, as it is our own technology. And we will switch the video to not to be too long of time. I will show you just 1 minute of the video, perhaps, just that you have an idea how such a unit is looking like. We switch down the sound. So it's a video that was made from the real unit standing in Baku in Azerbaijan. You can see here the reactor, here the knockout drum, then you have the off-gas treatment. Here is an extra Demalor unit we installed. The whole project was much bigger. Process unit. We had also the tank yard, laboratory, for control room, for operation and maintenance and everything. Here you can see the compressors, really important equipment besides the reactor and the indicator, because you need the air in a proper way. Here you see the tank yard for VR, the bitumen product, and the loading area on the bottom. Here, this big stack, it's not part of our project. It has been there, and it was not possible to destroy it because it would be much too dangerous and much too expensive. The client decided to let it where it was, but it's not necessary to have such. So we go back to the presentation. Also, another thing is the area is much bigger than the area we typically need. We can use much smaller area if you are short on space in the refinery. A few other references, just as a summary. In Europe and in Russia, we have 16 units in 10 different countries, producing mainly bitumen 3550 or 5070, but in Russia, BNB 6090 with a capacity of 5.5 million tons a year. The total bitumen production worldwide is approximately 20 million tons a year. Most of it is made, let's say 100 million is made on straight run or blending. And from the rest 20 million, let's say 12 to 13 million tons a year are coming out from Bitrox units. Two other references in the Middle East. We have 10 licenses in the Middle East, especially in Iraq, and then in Kuwait, Saudi Arabia. That's the biggest unit we ever built. We'll be starting at next month. And also in Oman, with a total capacity of 3.7 million tons a year. As a conclusion about SDA and Bitrox technology combined to produce bitumen and DAO. So as we said, it's a really efficient use of VR from several different routes. We can also use basic routes because it's working properly. We made a lot of testing on this, and it's really a good solution for countries like in Africa or in Asia, where they only have really basic route and they need a lot of bitumen. Using the Bitrox, the bitumen process with a composition controlled feed blending, we can really produce any kind of bitumen with high quality. So we can say as a conclusion, the combination of SD and Bitrox is the most cost-effective technology from bottom of the barrel to convert VR to valuable product. Thanks you a lot for your attention, and we will speak later on in the Q&A session. Bye.
Good afternoon. My name is Marvin Petitone, Global Sales Manager for IPCO. IPCO is happy to be here today to present our technology on the solidification of asphaltene pitch. Today, we will talk about IPCO's available technologies for the granulation of pitch. We'll present a comparison of the two technologies. We'll present a IPCO pilot plant for the pitch evaluation and testing. We'll discuss the pitch bulk solids handling system. We'll discuss IPCO's experience with the solidification of asphaltene pitch and also present a reference case for SDA pitch solidification. But first, who are we? IPCO is part of the Wallenberg Group with approximately 600,000 employees and over 140 billion euro in annual turnover. IPCO is present in 35 countries in order to be close to our customers for local support. Let's discuss the source of the pitch product. First, to begin our discussion, it is useful to actually define what the pitch is. Pitch is a waste stream from an upgrading process. Pitch is a mixture of complex asphaltene molecules, heavy metals, residual oils with a high carbon content. The pitch that IPCO typically receives from our process is basically from an upgrading processes such as solvent deasphalting, ebulated bed hydrocracking plus SDA, or slurry phase hydrocracking. The pitch properties are typically characterized by it being a high viscosity fluid with a high softening point. It is hard and brittle once it is solidified, thus making it an excellent solid fuel for CFB applications or as a gasifier feed. This flow diagram illustrates typically how IPCO receives the liquid pitch to our solidification process. The vacuum residue stream is typically fed to an ebulated bed reactor to produce light products. The unconverted oil stream at the bottom of the ebulated bed is fed to a solvent deasphalting unit or SDA unit. The deasphalted oil is physically separated from the pitch stream in the presence of a paraffinic solvent such as propane or pentane. The bottoms from the SDA unit, the pitch stream, is fed to IPCO's solidification process. IPCO has experience with working with all the major licensors such as CLG, Oxa, Honeywell, KBR, and others to provide solidification solutions for the pitch from their various upgrading processes. IPCO offers two technologies for the solidification of asphaltene pitch. The first technology is IPCO's pastillation technology. The pastillation technology basically produces individual free-flowing pastilles of liquid pitch. The process starts with the SDA unit. The pitch from the SDA unit is pumped into surge vessels. The surge vessels are actually kept hot, so the pitch inside the vessel remains molten. The pitch from the surge vessel is pumped through a positive displacement gear pump and through jacketed piping through filtration to the IPCO rotiform pastillation system. The rotiform pastillation system is a rotary depositor that deposits individual molten pastilles or pellets on a moving stainless steel belt. The pellets travel down the length of the conveyor and they solidify. Underneath the pastilles are deposited on a steel belt. The steel belt is cooled by cooling water. There is no direct contact between the cooling water and the individual pastilles. The heat from the pastilles are transferred from the pastilles to the steel belt and from the steel belt to the actual cooling water. The warm water from the process is collected in a pit or sump tank and sent to the plant tower system to expel the heat. As the pastilles travel down the length of the belt, they solidify into a free-flowing form and they discharge into the bulk handling system or packaging system. The second process that IPCO offers for the solidification of asphaltene pitch is our flaking system. The flaking system is based on IPCO's double belt technology. Identical to the pastillation process, the pitch from the SDA unit is sent to a surge vessel. From the surge vessel, the pitch is pumped through a positive displacement gear pump, through filters, into our casting box. The purpose of the casting box is to distribute a thin layer of pitch that's approximately 3 to 4 millimeters thick onto the lower cooling belt conveyor. The pitch sheet is sandwiched between an upper belt and a lower belt. Similar to the pastillation process, the sheet is cooled, but the big difference with this process, the sheet is cooled on both sides. Again, there is no direct contact between the sheet, the molten sheet, and the cooling water. The sheet is sandwiched between the upper belt and lower belt. The heat from the product is transferred to the lower belt and to the upper belt and transferred to the cooling water. And again, it is collected in a water pit or tank and sent to the plant tower system to expel the heat. The solidified sheet travels down the length of the conveyor and upon discharge it is fully solidified and cooled and is transferred to a product breaker for size reduction. We'll go into a comparison of the two technologies, pastillation versus flaking. Each offers distinct advantages and some disadvantages as well. The first biggest difference that you'll see is the picture on the upper right illustrates the production of pellets from the pastillation process. You can see that the pastilles are very uniform versus the randomness of the flake particle on the lower bottom right. Another big difference with the pastillation process is that the bulk density. The bulk density for the pastilles are roughly 65 to 75 pounds per cubic foot as compared to 40 to 50 pounds per cubic foot for the flake process, which offers a distinct advantage for packaging and shipping applications. However, one of the biggest advantages for the flaking process is regards to OPEX and CAPEX. The next slides will illustrate this advantage. One of the other biggest differences when we talk about pastillation versus flaking is, I will not go through every single point, but the biggest advantage, as you can clearly see on the bottom, is the capacity. The flaking process will produce 3 to 4 times more capacity on the same footprint versus the pastillation process. This advantage offers an extreme advantage when it comes to CAPEX. To illustrate the point of the CAPEX advantage of flaking versus pastillation, if you consider a reference plant for 500 metric tons per day of pitch, That will require approximately 5 trains or 5 units for the pastillation process. Each train or unit is roughly 1.5 meters wide with 40 meters of cooling. The required plot area would be 25 meters by 50 meters. Thus, if you compare that to the same reference plant for 500 metric tons per day for pitch or for flaking, that will require 2 double belt coolers with a plot plan of 12 meters by 50 meters. Instinctively, you can see that the plot plan is basically cut in half, and thus, because of the high efficiency of the double belt, that you're cooling the product from both sides, you can produce and run a lot faster versus pastillation. Thus, offers you an advantage when it comes to CapEx. In order to design these systems, either pastillation or flaking, IPCO operates 3 global productivity centers for the evaluation of liquid pitch. What you're seeing here is liquid pitch being fed onto a lower double belt cooler at IPCO's productivity center in Germany. The pitch is being fed on the lower belt and will be sandwiched by the upper belt. And as the pitch cools, as it travels down the lower belt, it solidifies into a sheet. And as you can tell, the sheet is very friable and very brittle, such that the flake pitch breaks on its own weight. Once the pastillation or flake of the pitch is actually solidified, it has to be stored. IPCO develops storage systems to handle the bulk pitch material. I will not go into every single point regarding that's on the slide, but one of the most critical aspects of storing, especially flake pitch, is the silo design. The silo must be specifically designed to handle the friable nature of the actual pitch. Thus, the silo height to diameter ratio must be considered. The materials of the construction for the inside wall of the silo must also be considered to provide a surface that has a low coefficient of friction to avoid any agglomeration inside the actual silo. IPCO has developed a specific silo design to manage pitch in order to make sure that our customers have free and clear operation without any problems with material rat holing or arcing inside the actual silo. As mentioned earlier, IPCO operates several different plants for pitch. We've chosen one specific plant to illustrate to the group a reference case for SDA pitch. This is a typical flow diagram of this plant. The plant basically was supplied with 12 steel belt cooling units to actually flake liquid pitch. The total capacity is under NDA, so I can't illustrate or mention the capacity. But 14 total machines were supplied to actually handle pitch. The scope of supply for IPCO included the 14 machines, the liquid pitch feeding system, the cooling water system, the exhaust system, the pitch breaker, and the solidifying the conveyor system. What you're seeing here basically is the liquid pitch being fed into the actual casting bar. The pitch is being fed into the actual casting box, and it's being collected, and it will be distributed onto a moving stainless steel belt. The next slide that you'll see is the pitch being transported on the stainless steel belt conveyor. And as you can see, the pitch is going down the length of the conveyor, and it is actually fully solidified and is being discharged into the actual product breaker assembly. Once the pitch is fully solidified and discharged into the breaker, it is transported from the steel belt conveyor onto a moving takeaway conveyor. And what you're seeing in this video is the pitch being on the transfer conveyor on its way to the storage facility. Okay, we thank you for this opportunity to allow us to present our solution for the solidification of liquid pitch. Please let me know if you have any questions, and please remember to try to schedule one-on-one meetings for more information on the topic. Thank you.